Hi everyone, let's talk about the inscribed angle theorem in geometry. There are usually four cases that are presented. So the first case is one that some people call the Star Trek theorem because of the shape of the inscribed angles. And it says that this angle up here is half of the angle down here. The second case is what is called Thales' theorem. It's where we have a diameter as well as an inscribed angle. And in this case, we have a right angle up here, which is half of the 180-degree angle down here. The third case has a reflex angle. So we have this reflex angle here. And if we have an inscribed angle, the inscribed angle is half the measure of the reflex angle. And the last case is analogous to the first case, but its diagram is different because we draw the inscribed angle like this. So this is the inscribed angle, and the central angle is here, and once again the central angle has double the size of the inscribed angle. Now usually what would happen in a proof is that these three or four cases would be tackled separately. Thales' theorem doesn't need to be tackled separately, although we have a separate video on that. But the other three cases need to be tackled separately. But what we're going to be doing is presenting a unified proof using complex numbers. And not only will we be proving all three cases using complex numbers, we'll be proving the converse, which establishes that this point up here, this point, we're going to call it P, that it lies on the circle if the half angle relationship is satisfied. So we're going to be proving both the forward direction and the backward direction using complex numbers. So let's do that. First we need a good diagram. So let's draw a big circle. And I'm just going to draw the Star Trek version because that captures the general idea. So the point up here, we're going to call it P, small p, because it's a complex number. The point down here, we're going to call it A. And the point down here, we're going to call it B. And the center, we're going to choose it to be the origin 0. It looks like an O, but it's a 0. And we're going to try to prove that this angle up here is half of the angle down here in all three cases. So what we're going to do is we're going to call A in polar form r times e to the I alpha, where alpha is the angle. B is r e to the I beta. And for P, since we are in one direction going to be proving that it lies on the circle, we're going to say that the distance from the center is s, but eventually we'll show that it's equal to r, s, and the angle is gamma. So those are our complex numbers. And what we want to investigate is angle APB, which we're going to call theta. And notice that theta is equal to the argument of b minus p. So b minus p is this vector. It's this vector. And that's going to be over a minus p, which is this vector. So we're going to do b minus p over a minus p, and we're going to call that t times e to the I theta. And theta is what relates it to the inscribed angle. And if we use substitutions, we get that this is equal to r e to the I beta minus s e to the I gamma divided by r e to the I alpha minus s e to the I gamma. Now the trick that we're going to be using is we're going to take the conjugate of this equation. So if we take the conjugate of both sides, we get that t e to the I negative theta is equal to r e to the I negative beta minus s e to the I negative gamma divided by r e to the I negative alpha minus s e to the I negative gamma. And now we're going to multiply both the top and the bottom by e to the I beta, e to the I gamma, and e to the I alpha just to get rid of the negatives. And what that gives us is r e to the I alpha times r e to the I gamma minus s e to the I beta divided by r e to the I beta times r e to the I gamma minus s e to the I alpha. And what we're going to do now, we're going to take this first equation, we're going to take the second equation, and we're going to do 1 divided by 2 so that we can get rid of the t. We don't care for this magnitude t, it doesn't matter to us. So that'll let us get rid of the magnitude t. So what we get in that case is e to the I 2 theta, because theta minus negative theta is 2 theta, is equal to r e to the I beta minus alpha, because of this part we just combined it, and then what we get is this times r e to the I beta minus s e to the I gamma divided by r e to the I alpha minus s e to the I gamma. And then we're going to be multiplying by r e to the I gamma minus s e to the I alpha divided by r e to the I gamma minus s e to the I beta. Now what we're going to be doing is working on each of the two directions separately. So for the forwards direction, what we're going to say is that r equals to s, because that's when p lies on the circle. So if r equals to s, what happens is that we get some cancellations. So let's write out this equation over again with r equals to s. We get e I to the 2 theta equals, the r here should actually have canceled out, so we'll cancel that out since the two r's here cancel out. We get e to the I beta minus alpha times r e to the I beta minus r e to the I gamma divided by r e to the I alpha minus r e to the I gamma times r e to the I gamma minus r e to the I alpha. So you can already see some cancellations here, times r e to the I gamma minus s e to the I beta. So these two cancel out. We get cancellation here and here, that produces a -1, and here that produces another -1, so we get just 1. So that gives us e to the I 2 theta is equal to e to the I beta minus alpha. And that means that 2 theta is congruent to beta minus alpha mod 2 pi. But notice that theta is an inscribed angle, so 2 theta is in 0 to 2 pi. And beta minus alpha is a central angle, so it's also in 0, 2 pi. So that means that 2 theta is actually equal to beta minus alpha, which is what we were looking for. So let's do the other direction now, where we're going to be assuming that 2 theta is equal to beta minus alpha. What that gives us in our previous equation is that, I'm just going to scroll up for a second, because what's going to mean is that this part and this part are going to cancel out. So we're just going to be left with this part here. So let's work with that. What we get by canceling those two parts out and by clearing the denominators is that r e to the I beta minus s e to the I gamma times s e to the I alpha minus r e to the I gamma is equal to r e to the I alpha minus s e to the I gamma times s e to the I beta minus r e to the I gamma. And now we're just going to expand out both sides. So we get rs e to the I beta e to the I alpha minus r square e to the I beta e to the I gamma minus s square e to the I gamma e to the I alpha plus rs e to the I gamma e to the I gamma. And on the other side we get rs e to the I alpha e to the I beta. So we can see we're going to get some cancellations on the two sides. Minus r square e to the I alpha e to the I gamma minus s square e to the I gamma e to the I beta plus rs e to the I gamma e to the I gamma. So let's see our cancellations. We cancel out the first terms. We cancel out the final terms. And now we're gonna move everything over to one side. So we get r square minus s square e to the I gamma times e to the I alpha minus e to the I beta is equal to 0. And e to the I gamma can't be 0, so we can cancel it out. And alpha and beta are different angles within 0 and 2 pi, so we can cancel that out. And what we're left with is r squared equals to s squared, and therefore r equals to s. So that proves that P is on the circle. Thank you for watching, and I'll see you next time.